Hi, I am Anthony Mark Cortez. For today's agenda, we will be discussing topics inclined with general physics 2, namely electrostatics, structure of the atom, process of charging, Coulomb's law, electric field, electric lines of force, electric field due to point charge, electric potential and potential difference, and capacitors. Starting with electrostatics. Electrostatics is a branch of physics that deals with the phenomena and properties of stationary or slow-moving electric charges. Electrostatic phenomena arise from the forces that electric charges exert on each other and are described by Coulomb's law. Even though electrostatically induced, forces seem to be relatively weak. In 1600s, William Gilbert, who served as a physician to Queen Elizabeth I of England, found out that many other substances possess the same ability as that of amber when rubbed against each other. He called these substances electrics and this ability of amber electricity, from the Greek word electron, which means amber. This is the structure of the atom. To understand the electrostatics, the structure of the atom must first be understood. An atom is made up of subatomic particles, protons, neutrons, and electrons. Protons and neutrons constitute the nucleus of an atom while electrons orbit an atom nucleus. Properties of proton, neutron, and electron. The table shows the location, mass, and charge of subatomic particles, which consist of proton, neutron, and electron. Process of charging. It occurs in three main ways: friction, conduction, and induction. In friction, two objects rub against each other, transferring electrons, so one becomes negatively charged and the other positively charged. In conduction, a charged object touches a neutral one, transferring charge, so both of the same charge. In induction, a charged object is brought near a neutral object, causing charge rearrangement. If grounded, the neutral object becomes oppositely charged. In charging by friction, results when two different materials are rubbed together. The material that will either become positively charged or negatively charged depends on its electron affinity. Electron affinity is a measure of the attraction of an atom to an electron, or the tendency of an atom to become negatively charged. Charging by friction. Triboelectric series is arranged in an order of increasing electron affinity from top to bottom. In general, when two different materials are rubbed together, the one that is higher on the list will become positively charged. Charging by conduction is a process of charging wherein electrons are transferred from one object to another by direct contact. The image presents how charging by conduction process. Charging by induction. The induction charging is a charging method that charges an object without actually touching the object to any other charged object. Coulomb's law. All charges particles attract or repel one another depending upon their nature. Generally, like charges repel and unlike charges attract. Coulomb's law determines the electrostatic force of an attraction or repulsion between them. Charles Augustin de Coulomb invented a device dubbed the torsion balance that allowed him to measure very small charges and experimentally estimate the force of attraction or repulsion between two charged bodies. Through experimentation, Coulomb discovered that the magnitude of the electrical force between two charged particles is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. This statement is called Coulomb's law. Mathematically, this can be written as F sub E is equal to K absolute value of charge 1 and charge 2 over distance squared. Whereas F sub E is the magnitude of the electric force in newtons, and charge 1 and charge 2 are charges in coulombs, and these are the magnitudes of the two charges. R represents the distance between the center of two charges in meters, while K is the proportionally constant called Coulomb's constant with an approximate value of 9.0 times 10 raised to positive 9 newtons dot meter square slash c squared. The electric force is a vector quantity which may be positive or negative depending on its direction. Coulomb's law bears a strong resemblance to Newton's law of universal gravitation. Both equations have the same form. Recall that the gravitational force between two masses is given by m sub g is equal to constant by mass 1 and mass 2 under distance squared, where g is the universal gravitational constant, approximately equal to 6.674 times 10 raised to negative 11 newton meter squared slash kilogram squared. Example number 1. Two small charged spheres, each of mass 0.2 kg, are suspended 1 meter apart in space. One has charge of positive 5 times 10 negative 6 coulomb, and the other has positive 3 times 10 raised to negative 6 coulomb. Find the magnitude of the electrostatic force of the gravitational force between them. For the givens, these are the givens, and for the solution, F sub E is equal to the K, which is the constant value of coulomb, and the two charges with the absolute value between them, over 1 meter squared. So if we multiply the two charges and apply the absolute value divided by the 1 meter squared, it will be 15 times 10 raised to negative 12 meters and c squared. So if we multiply the constant value of column times 15 times 10 raised to negative 12, it will be 0.135 Newton. The meter squared and c squared will be cancelled. So the magnitude of electric force will be 0.135 Newton. For the gravitational force, we must use the formula of gravitational force. So F sub g is equal to constant value of gravitational force, and for the mass 2 and mass 1, which is 0.2 kilogram over 1 meter squared. So if we multiply, square, and divide this fraction, we will come up with the 0.04 times the constant value of gravity, which will sum up into 2.67 times 10 negative 12 Newton. For the example 2, to sum up, these are the givens. For the solution, again, we will use the electric force formula. F sub E is equal to constant value of column times the absolute value of 6 times 10 raised to negative 6 column. And the other charge is negative 2 times 10 negative 6 column divided by the 0.4 meter squared, which we will come up with 12 times 10 raised to negative 12 column divided by 0.16 meter squared times the 9.0 times 10 raised to 9 Newton dot m squared and c squared. So we will cancel the meter squared and c squared, which we will come up with 0.675 Newton. For the example 2, again, these are the givens. So for the solution, S of g is equal to the constant value of the gravitational force times the two masses divided by 0.4 meters squared. So if we come up with the solution, we will come up with 1.4 times raised to negative 12. For the example 3, to sum up, these are the givens. So for the solution, F sub E is equal to the constant value of electrostatic force, or I mean column, which will times to the absolute value of the two charges, 8 times 10 raised to negative 6 column, times 5 times 10 raised to negative 6 column, divided by 0.5 meter squared. So for the solution, which will be come up with 1.44 Newton. For the gravitational force, so these are the givens. For the solution, F sub g is equal to the constant value of gravitational force times the two masses divided by 0.4 meter squared. So if we calculate this, we will come up with F sub g is equal to 2.67 times 10 raised to negative 12 Newton. Electric field. Electric field is an non-contact force. An electric charge Q can exert force on other charged objects even though they are at some distance away. The space surrounding charged body is called an electric field. An electric field causes any charged particle placed it on to experience an electric force. Every charge has an electric field associated with it. For example number 1, these are the givens. Then we must use the electric field is equal to charge times the electric force. So in determining the electric field, we must multiply the charge and the electric field associated with it. So negative 2 times 5 Newton or Coulomb is equal to negative 10 Newton. Example number 2, these are the examples or the givens. So we must again multiply 0.5 Coulomb times 12 Newton per Coulomb is equal to 6 Newton. For the example number 3, again these are the givens. So we must determine the electric field. So the positive 2 charge times 8 Newton per Coulomb is equal to 16 Newton. So for the electric lines of force, Michael Faraday was an English scientist who made important contributions to the fields of electrochemistry and electromagnetism. The concept underlying electromagnetic induction, diamagnetism, and electrolysis were among his most important discoveries. What are the properties of lines of force? For the electric field due to point charge, an electric field can exist in the region of space around a charged object or a source charge. The strength of the electric field at a point charge is called electric field intensity. This is the magnitude of the electric field due to point charge. As you can see, the electric field due to point charge is equal to the constant value of Coulomb times the absolute value of charge divided by the distance squared, where E is the magnitude of electric field in Newton or Coulomb, K is the Coulomb's constant, and the absolute value of Q is the magnitude of the point charge in Coulomb and or charge, and for the distance is represented by R squared is the distance from the charge to the point where the field is measured in meter. Example number 1. To sum up, these are the givens where K for the constant value for the charge is negative 4 charge and for the distance is negative 8 meter. At the electric field due to point charge, we will use the formula given. So we multiply the constant value of Coulomb times the absolute value of the charge, which is negative 4 C or charge, over or divided by 8 meters squared. So for the answer is 5.63 times 10 raised to positive 8 Newton per Coulomb. For the example 2, again these are the given. We will use again the formula for electric field due to point charge. So calculate again. So the constant value times the absolute value of the charge, 6 charge divided by 5 meters squared. So for the answer, 2.16 times 10 raised to 9 Newton per Coulomb. For the example 3, again we will use these givens and for the formula. So for the solution, electric field due to point charge, the constant value of the Coulomb times the absolute value of negative 2 charge divided by 10 meters squared. So the negative 2 charge, it will become positive 2 charge because of the absolute value. So if we calculate it all, it will become 1.8 times 10 raised to 8 Newton per Coulomb. Electric potential and potential difference. Electric potential, also called electrostatic potential or potential at any point in electric field E. It is designated as V, a scalar quantity. Its SI unit is the volt V, named after Italian physicist Alessandro Volta, who devised of the first electric cells. Potential difference, often referred to simply as voltage, is the difference in electric potential between 2 points in electric field. So this is the formula for potential difference. E is the electric field in volts per meter, and the triangle is the potential difference between the point, and for the D is the distance between the 2 points in meters. Example number 1. Again, point A is 5 meters from the charge and point B is the 8 meters from the charge. So a point charge of negative 10 times 10, negative 6 Coulomb or negative 10 microcoulomb is placed in space. Find the electric potential at points A and B and find the work done by electric field in moving a 3 nanocoulomb particle from point A to point B. So these are the givens. So for the electric potential, we must multiply the constant value of Coulomb, the charge negative 10 times 10 raised to negative 6 Coulomb divided by 5 meter. Again, this is V sub A. So if we sum up, the V sub A is equal to negative 18.0 kV. And for the distance of V or the electric potential sub V, B Again, we will multiply the constant value of Coulomb times the charge divided by 8.00 meter. So the answer will be negative 11.25 kV. For the potential difference, we will subtract the V sub B minus V sub A. So the answer would be 6.70 times 10 raised to positive 3 volts. For the work, this is the formula. 3.00 times 10 raised to negative 9 times 6.75 times 10 raised to positive 3. So the answer will be 20.25 times 10 negative 6 joule. Sample number 2. Again, take note the 2.00 nano Coulomb. We will use that in determining the work. So this is the givens. Again, we will multiply the constant value of Coulomb times the charge divided by 3.00 meter. So the answer will be negative 15.0 volts. And for the V sub B is equal to the constant value of Coulomb times the charge divided by 7.00 meter. The answer will be V sub B is equal to negative 6.43 volts. For the potential difference, again we subtract, so the answer will be 8.57 times 10 raised to positive 3 volts. For the work, 2.00 times 10 raised to negative 9 times the 8.57 times 10 raised to positive 3, which is the potential difference. So the answer will be positive 17.14 times 10 raised to negative 6 joule. The example number 3, again we will take note the 4.0 nano Coulomb. So this is the givens. So for the V sub A, again multiply, divided by the R sub A, which is the 4.00 meter, and multiply the constant value of Coulomb and the charge. So the answer will be positive 18.0 volts. And for the potential point at B, again multiply, and for the distance, or the R sub B is 10.00 meter. So the answer will be 7.2 volts. The potential difference, again, subtract. So the answer will be negative 10.8 times 10 raised to positive 3 volts. For the work, again, we will apply the 4.0 times 10 raised to negative 9 because it's nano times the answer of the potential difference. So the answer will be negative 43.2 times 10 raised to negative 6 joule. Capacitors. When connected to a source of charge, such as battery, the positive terminal of the source removes electrons from the plates connected to it, transfers them to the other plate. As a result, the two are equally but oppositely charged. Figure shows that the basic parts of a parallel plate. A capacitor is usually named after dielectric material used. Common dielectric materials used in a capacitor are mica, glass, air, ceramic, and paper. Capacitance. Capacitance is the ability of a capacitor to store charges. The capacitance of a capacitor is mathematically defined as the ratio of the amount of charge Q in one plate to the potential difference between the plates in symbols. So this is the formula. For the C is the capacitance in farads, Q is the charge stored in coulombs, V is for the voltage across the plates. The dependence of the capacitance of a parallel plate capacitor on the factors cited is mathematically expressed as C is equal to the permittivity of area divided by the separation between the plates in meters. So this is the process of the capacitance on how it works. And this is the value of the dielectrics. Air or vacuum is equal to 0.885, glass, ordinary glass is equal to 7 for the permittivity, and for the glass 4.7, mica 4.8, mylar is 2.7, paraffin is 2, polyethylene is 1.99, and so on. Example. A capacitor consists of 2 square metal plates, each measuring 9.00 times 10 raised to negative 3 meter on the side. In between the plates is straight porcelain measuring 3.00 times 10 raised to negative 6 meter thick. What is the capacitance of this capacitor if 10 charge is in one plate is 7.00 times 10 raised to negative 9 coulomb? And find the potential difference and electric field between the plates. So these are the givens. In finding the capacitance of the capacitor, we must use this formula. C is equal to the permittivity of the dielectric area divided by the distance in meters. So the area of the plate is squared, so the area will be 8 times 10 raised to negative 5 meters squared. So for the capacitance of the capacitor is equal to 6.5 times 10 raised to negative 11, which is the porcelain, times the area, which is 8 times 10 raised to negative 5 meters squared, divided by the distance. So the answer will be 1.73 times 10 raised to negative 9 farads. And for the potential difference, we will divide it. So 7.00 times 10 raised to negative 9 charge divided by 1.73 times 10 raised to negative 9 farads, it will be 4.5 volts. For the electric field between the plates, we will use this formula. E is equal to the volts divided by the distance. So 4.5 volts divided by 3.00 times 10 negative 6 meter. So the answer will be 1350000 volts. Combination of capacitors. Capacitors can either be in series or parallel. Referring to the figure, the series combination of capacitor is characterized by only one path for charge transfer through materials A and B. All the series capacitors acquire the same charge. The charges in each capacitor are equivalent and are all equal to the total charge in the combination. But because they are different capacitors, the potential differences between the plates of the capacitor are different. In summary, the following relationship apply the capacitors in series. For the charge, the Q total is equal to Q1, and so on, and for the potential difference, and for the capacitance. For parallel capacitors, these are several paths for the transfer of charges through the voltage terminals A and B. Since the capacitors are connected to the same terminals A and B, the potential differences between their plates are equivalent and are equal to V total. So, for the example number 1, for the capacitors in series, 3 capacitors, C1 is for 4 farads, and C2 is for 6 farads, and C3 is for 12 farads. What is the total capacitance and the charge on each capacitor and voltage across each capacitor with a 24 volts battery? So, these are the givens. What is the total capacitance? Formula. And for the total capacitance, we must add them. Then, after we add them, we must cross multiply it. So the answer will be 2 farads for the total capacitance. For the charge on each capacitor, we will use the formula Q is equal to the total capacitance and total voltage. So we must multiply it. So 2 farads times the 24 volts will be 48 volts. For the voltage across each capacitor, this is for the formula. So V sub 1 is equal to 12 volts. For the V sub 2 is equal to 8 volts. And for the V sub 3 is equal to 4 volts. So sum them up. So we will come up with 24 volts. Example number 2. So sum up these are the givens. Again, we will find total capacitance at the 3 capacitors. So 0.611. So we will cross multiply again, then cancel. So the total capacitance will be 1.64 farads. To determine the charge on each capacitors, we will multiply again the total capacitance and the total voltage. So
1.64 farads times 30 volts is equal to 49.2 volts. And finding the voltage across each capacitor, this is the formula. For the V sub 1 is equal to 16.4 volts, and for the V sub 2 is equal to 8.23 volts, and for the V sub 3 is equal to 5.47 volts. So sum them up, 16.4 volts plus 8.23 volts plus 5.47 volts. So the answer will be 30 volts. For the example number 3, again these are the givens with the 20 volts. So in finding again the total capacitance, we must use this formula and sum them up. So we will come with 0.8. So we must cross multiply it, and we will come up with the total capacitance 1.25 farads. For the charge on each capacitor, multiply again 1.25 farads times 20 volts is equal to 25 volts. And for the voltage across each capacitor, for the V sub 1 is 12.5 volts, for the V sub 2 is 5 volts, and for the V sub 3 is 2.5 volts. Then sum them up, so the answer will be 20 volts.
On to the capacitors in parallel. So these are the givens. In determining the total capacitance, we will sum up the three capacitors. So the answer will be 17 farads. For determining the charge on each capacitor, we must multiply the charge and the volts. So for the charge 1 is equal to 40 coulomb, and for the charge 2 is 100 coulomb, for the charge 3 is 200 coulomb, and for the total charge, 40 coulomb plus 100 coulomb plus 200 coulomb will be 240 coulomb. So the voltage across each capacitor will be 20 volts. For the example number 2, these are the givens. In summing up the total capacitance, which will be 18 farads. So in charge on each capacitor, we must multiply the capacitor times the volts. So for the first charge is 3 farads times 15 volts is equal to 45 coulomb. And for the Q sub 2 or the charge 2 is equal to 90 coulomb. And for the Q3 or the charge 3 is equal to 135 coulomb. And sum them up, so you will get the answer 270 coulomb. And for the total voltage or the voltage across each capacitor will be 15 volts. For the example number 3, again, these are the givens. For the total capacitance, just sum all the capacitors and we will come up with 24 farads. For the charge on each capacitor, charge 1 is equal to 40 coulomb. For the charge 2 is equal to 80 coulomb. For the charge 3 is equal to 120 coulomb. For the total charge will be 240 coulomb. For the voltage across each capacitor, we will come up with the given volts, which is 10 volts. Combination of capacitors in series and parallel connection. For the example number 1. So these are the givens. The C1 and C2 are in series, and for the C3 and C4 are in parallel with 12 volts battery. So these are the givens. First step, we must add the C3 and C4 or C sub 3 or C sub 4 or the capacitor 3 and 4. It's because it's in parallel connection. After summing them up, we will come up with 9 farads. Then calculate it like in series method. So next step will be determining the total capacitance. So sum up all the capacitors C sub 1, C sub 2, C sub 3 and 4, which is 2 farads plus 4 farads plus 9 farads. We will come up with 0.86 farads. Then cross multiplication and cancel the 0.86. In the right side, we will come up with 1.16 farads in total capacitance. For the charge on each capacitor, we must multiply the capacitance or the total capacitance and the voltage. 1.16 farads times 12 voltage, we will come up with 13.92 volts. Then we will find the voltage across each capacitor. So we will use this formula. Then for the V sub 1, which is 13.92 volts divided by 2, is equal to 6.96 volts. And for the V sub 2 or the volts 2, we will come up with 3.48 volts. And for the V sub 3, for 1.546 volts. For the voltage across each capacitor, we will sum them up all the total voltage to determine the total voltage. So the total voltage will be 12 volts. Example number 2. Again, this capacitor 1 and 2 are in series, and this capacitor 3 and 4 are in parallel. They are connected across 24 volts battery. To sum up, these are the givens. Again, sum up this capacitor 3 and 4 because it's in parallel connection. For the next step, again, total capacitance, sum all the total capacitance to determine the total capacitance, sum all the capacitors, then cross multiplication. And after the cross multiplication, we will cancel the 0.67 in the right side to determine this total capacitance. Then 1 divided by 0.67 is equal to 1.49 farads, which is the total capacitance. For the charge on each capacitor, we will multiply the total capacitance and voltage. So the answer will be 35.76 volts. Then we will again find the voltage across each capacitor. We will use this formula. So for the V sub 1 is equal to 11.92 volts. For the V sub 2 is equal to 5.96 volts. And for the V sub 3 is equal to 5.96 volts. Because the capacitor 2 and 3, 4 are both 6. And for the voltage across each capacitor, again sum all the capacitor. Then we will come up with the answer 24 volts. For the example number 3, and these are the givens. As usual, the C sub 1 and C sub 2 are in series, and for the capacitor 3 and 4 are in parallel with the 30 volts. Again, because this capacitor 3 and 4 are in parallel connection, we will sum them up. So the answer will be 12 farads. Again, we will determine the total capacitance. So sum all the total capacitance or the capacitors, we will come up with 0.38 divided by, we will cross multiplication. So, and then we will cancel the 0.38. Then divide the 1 farad divided by 0.38, we will come up with 2.63 farads in total capacitance. For the charge on each capacitor, again we will multiply the total capacitance and the voltage. So 2.63 farads times 30 volts is equal to 78.95 volts. For the voltage across each capacitor, we will again use this formula. For the V sub 1, 78.95 volts, which is the charge, divided by 5, which is the value of capacitor 1. So the answer will be 15.76 volts. For the V sub 2, 30 again, but again, this is the capacitor 2, which is 10. So the answer will be 7.895 volts. For the V sub 3, this is the capacitor 3 and 4, which is valued 12, is equal to 6.58 volts. For the voltage across each capacitor, So, to determine the total volts, we will again sum up all the total voltage across each capacitor. Then we will come up with the total voltage, 30 volts.